let me just begin with the presentation here and who we are. We are 3 Brazilians, and at the time we worked at Sprout AI. I'm going to present myself. I'm going to allow my teammates to present them too. So my name is Mateus, and I've been working at Sprout AI for 3 years now, and I've been at Kaggle 5 years, around that. Yeah, we worked a lot with vision before, but now I had to change to LLMs, so we got a job, you know. So, but that's about it. Also, I wanted to give a huge shout out to my friend Eduardo. He was the one who presented Kaggle to me. So please go on, man.
Yeah, nice to meet everyone. My name is Eduardo. I'm also an electrical engineer by graduation, but I changed to machine learning. And actually, a fun fact: like most of my career change was driven by Kaggle. Like Kaggle was one of the first thing I noticed when I was getting interested by data science. So it was really a huge boost for me, and like I learned a lot in Kaggle. And then I changed to data science. One of the reasons was it. So most of my expertise is also in computer vision, a bit more recent with natural language processing. Yeah, that's pretty much it from me, Pedro.
Yeah, hi everyone. I'm also Brazilian, but I'm based in Italy actually. I live in Rome. I'm also a senior data scientist at Sprout. Been there for about 3 years. Like the other guys, also had background in computer vision and now moving a bit more towards NLP. I am a computer engineer by my bachelor's in computer engineer, and I have a master's in data science as well. And yeah, I've been in Kaggle for a long time now, since I was doing my bachelor's, maybe 10 years, but I haven't done a competition in quite a while. So this was the first one, I think, in the past 4 years. So it was a very, very good to be back. And yeah, that's it.
Yeah. Great. Let me just move on. So basically, our solution is just a main prompt, and that's it. I'm kidding. So basically, a few things that we did in our solution is we have a main prompt, of course, and I think everyone here will probably have a main prompt in between. But let's talk a little bit about it before. So we also fine-tuned a couple LLMs, and I'm going to get in more detail later. But basically, we had 3 or 4 LLMs, one for generating the full prompt, which we tried for a long time to just generate the full prompt and do regular predictions by generating some data sets. We had some shortcomings on that. I can get into more detail too. We also have some model that was very similar to was presented by the second place, which we call tags here, but it really is the core of the prompt, right? Like the intrinsic part of the prompt, excluding the style or something like a rewrite or reword or put into other words, something like that, right? And also we have a gate model to exclude blatantly wrong predictions. And finally, 2 clustering models that use right at the end that something that we thought had a lot of potential, but we could not really get much results out of this. We did get some improvement that was definitely necessary, given how the leaderboard was cramped together. But we could have gotten like a couple more out of this, but we just couldn't make it work so much. But yeah, like it was definitely necessary in the end. I'm gonna go to about the general pipeline. I'm gonna come back to this image later, just giving an overall flow of what I did. So basically, we have given the original text and the written text, we predict the full prompt that was to generate it, and then we have a gate model, and then we have some way to merge our predictions to mean prompts. I'm going to get more detail later, but it's very similar to the second place solution in some sort of sense, because we basically have the mean prompt and we add to it the predictions of some models in some structured way. So I'm going to be coming back to this image later, but that's basically the overall point of the solution. Okay. So about the mean prompt, right? So I think the first month of the competition, we all only tried to fine-tune the models. That is, trying to generate some data and trying to get the full prompt out of it, like in a standard way. And it was really hard to get something that was beyond the mean prompt. You rewrite to this, basically was beating any model that we had, and there was like a little bit bad for our confidence in the beginning, because we couldn't make a model to work right in the beginning. And then we have a brilliant idea from Pedro, which is basically trying to fit a local data set to the private data set of the competition, and basically trying to select a subset of data that was very representative to the data that we have in the competition. Because we noticed that the results for mean prompts were not really matching the results from LB to the public data that we have in the competition. Basically, we have like 30, 40,000 examples public that a lot of people shared in the competition. And we just noticed that both that data set and any data set that we generated too did not match very well with the mean prompts that we had at the private, at the LB or private, right? They're not really matching really well. So basically, a mean prompt will not get the same score as they get in LB as they get in our local data sets, basically. And so what we did is, let's get a data set that matches that, right? So we got a few examples, both that are public, like a lot of people sent a lot of mean prompts. I thought that we have a lot of mean prompts there in the competition, plus some that we tried to, and we got a bunch of scores out of this. And what we did is giving a list of those scores. I think at the end we had like around 20 few, something like that. So at the end, with all those points, we basically run an algorithm to select from our local data set a subset that had the same scores for each mean prompt. And that ended up working really, really well, to the point that any mean prompt that we have locally matched almost exactly at the LB, and both private. We later saw that it matched almost exactly. And the reason it didn't match better is because here we only have 2 decimal places since the beginning of the competition. And then the way we estimated was considering that it was rounded to this value. But in the end, we noticed it was floor and not round. So we are always 0.005 of both private from the LB, almost consistently this the expected difference between floor and average. But in the end, it worked really well. And maybe Pedro can explain a little bit more about the details of this algorithm if you guys have some questions later. But after selecting this data set, which is kind of small, I think in the end we use 1,300 examples only. This small data set, which is similar to the size of the private too. I think, sorry, 1,800, very similar to the size of the private. We also run a very simple algorithm on this data set to select what is the best mean prompt for this data set. So we have this small data set, and now we can optimize for it very simply using a bin search. This is very simple. Basically, select for each step what is the token out of a selected part. We don't use the 32,000 tokens. We use only a small part of it. We select which ones they give the best score, and we run a bin search up to 50 tokens. And that was about it. And we got almost 0.7 out of this mean prompt. We could have got a little bit better, but we noticed that the better the mean prompt got, the less effect our models had on the results. So the larger the mean prompt, the less effect our predictions had. So about the predictions and about the models that we did, so this full prompt model is basically, we struggled a lot in the beginning to get a model that achieved 0.6.2 alone. So this is prediction alone, right? Like without tags, without anything, the full prediction. And we noticed there was a lot of noise into the prediction in the style itself and not in the content of the prompt. So basically changes in the style gave much lower scores than, for example, changes in the content, for example. So it was really hard to predict like the full thing to get high scores here. We noticed that Mistral was much better, and also this final version was better than the 0.1 version, 0.2. Like as a drop-in replacement, this model was much better. And everything that we did was using a single GPU, a single 4090. Also, we use Unslot for training, which is very, very efficient regarding both memory and time. We managed to use like a batch 16 with a 4090, and that's the only thing basically used throughout the whole competition. I think Pedro used a different GPU, but we could have gotten away with using a single 4090 anyway. And then basically, we iterated through this model from the beginning to the end of the competition by generating a lot of data, by generating variations of the same prompts, by filtering using clustering, by using different validations locally. So it was a very long process. So from the beginning of the computation to the end, we were training models to get the best one. We also have a gate model, which is basically trained in such a way that it can remove predictions that are very wrong. They're clearly wrong. One thing that we notice is that sometimes the model just outputs something very similar to the written text. So basically, we have the original and the rewritten, and it outputs something very similar to the rewritten. So that would be like a blatantly wrong prediction. Other times, it just overfeeds a little bit with our training and exports something that has nothing to do with the predictions. So having a gate model here to exclude clearly wrong predictions was beneficial. Again, the improvement on that was a little bit, but very consistent and definitely necessary to, given how cramped and how competitive it was. Also, we have a text model, which is very similar to the model that the previous team had, which is basically exporting part of the prompt, like the core of it, the core idea of the prompt. So we also use the same model here, and we removed anything that is common between the full prompt and the tags, right? Let me go a little further. So yeah, clustering. This is the last thing we tried in the end. I'm going to take a little bit of time to explain what we're doing here. So basically, after we have this local data set that is very similar to the private data set regarding the mean prompts, what I notice is if we were to find a single embedding in this data set that had the highest score, and we can do it like by direct optimization, we can find a mean prompt, an embedding for a theoretical mean prompt that achieves 72. So this is probably the highest score, the upper bound of the score that you can achieve with a single prompt in that data set that is very similar to a local one. But this is probably not true because this is the embedding itself. So there is some loss into decoding it to actually get a stream. But this gives us an idea of how further we can go with the mean prompt alone. So we're very, very close to reaching like the maximum that we could get with a mean prompt, because we had like mean prompt 0.695. So this was very close to the upper bound of what we could have. But the thing is, if we could split the data in such a way that we could have more than one mean prompt, we could increase this a lot. And the idea is, given that we have your data set, if you could split it in such a way that you could use a mean prompt for a part of it, for each part of it, each cluster of it, you could use one mean prompt, a different mean prompt, we could push this result much further because the data has like we could split the data in such a way using clustering and estimate like not one mean prompt, but n mean prompts, multiple mean prompts, right? And that was theoretically much higher. The issue is how we assign which mean prompt you want for each data, right? For each point of the data, because we also have some error here. Even though if we were to use more than one mean prompt, we need to select which mean prompt to use, right? And for this, we trained a model to do that. And at inference, we also use a k-means to basically a small ensemble here to decide whether or not we are going to use the mean prompt for that cluster or a general mean prompt. So this is a little bit complicated, but it was definitely necessary in the end, even though the increase in performance not a lot, just because again the leaderboard was so cramped. So it definitely worked in the end and definitely necessary for a solution too. So I'm going to come back up here at the image just to show an overall, just to overview what we did. So basically, we had a full prompt, and we had a gate after that, just to exclude predictions that we know for sure were wrong. And then we had a selection of which mean prompt to use. We can use the mean prompt selected for the clusters, which we selected locally. We optimize in the same way. We clusterize the data locally. We select 12 mean prompts in the end. And then we select which of those 12 mean prompts to use by a small example of a model and a k-means clustering locally inside the notebook. And if they don't agree, we just use the global one. If they agree, we use the mean prompt for that cluster. And we merge that together with the text model and remove any overlapping words. And that's it. That's our final solution. So just to close it up, important findings, right? So we noticed since from the beginning that combining the mean prompt was very effective. And we noticed this because even without using fine-tuned models, we got really good scores by using zero shot or few shot by adding the predictions into a mean prompt. So that since from the beginning, we got our best results by getting a mean prompt and add something to it, right? Also, fine-tuning was very challenging. In the end, we could not manage to get like very strong models by just fine-tuning directly. We got some improvement from the beginning of the competition, but we definitely needed to use mean prompt and probably almost everyone else. What really helped us was how well the data was generated and curated since from the beginning. And as well, yeah, in the end, the clustering, that helped a little bit, but had a lot more potential. And just to finish it up, a simple model would be this mean prompt, we achieve 0.695, and it's very clean. So we were a little bit afraid of using like prompts that are not like, it makes no sense. It makes zero sense, but it only contains words that are like a lowercase and some stuff like this. We're a little bit afraid of using something that was completely crazy here, just for overfitting. But you notice that if we estimated a mean prompt for a subset of the data, which is exactly how the LB is extracted from the private, is a random subset. As the I think the competition host had a post about that, and they were very consistent if we estimated on a subset of the data. So yeah, this is our final solution, and probably a simple solution would be to use this mean prompt, and these two first models would be a very simple solution if we had to use like a simpler solution. But in the end, we had to use more stuff to squeeze the little bit, the last part of it. Yeah, guys, that's it for me. If Eduardo want to say something, that's about it.
Thank you. Well done. Great. Open for any questions from any team. No questions? Then maybe I have one here. So can we go back to the gate model?
Of course.
Yeah, thank you. I'm interested to learn, so you mentioned like the gate model, I found it interesting. So I wonder, like you mentioned, is beneficial for the whole overview of the, like the model, the scores, but what if we don't have this gate model? Like, what would you think like the outcome would be?
Do you want to talk a little bit more about this, Eduardo? Maybe?
Yeah, sure. So basically, one thing that we noticed is that since we have a very strong mean prompt as template, even if we add the tags in the end or even the full prompt prediction, and it's completely wrong, this will penalize the score, but not that heavily because it's already a very long sentence, and the way that T5 is embedding that, it's pretty kind of like is not shifting too much from the template itself, right? By adding just a few words. But what we found is that there are some cases where the model that predicts the full prompt make mistakes that are very easy to be spotted. And I think this is usually due to overfit because the training data that we had and that we used to fine tune the models has a certain degree of diversity, but of course not perfect. So whenever it makes a prediction, it's usually to a prompt that was seen in the training data. Is like it kind of loses the ability to extrapolate much beyond that, we notice. So sometimes we have a test sample that is very different and similar for what it saw in the training data, and then it predicts a prompt that's completely way off. And then what we did is just to train a Mistral for classification. So basically, we give a triplet as input: the original text, the predicted prompt, and the the final output text. And then this model simply classifies if that prediction is likely to be correct or not. And then this model helps to remove, filter out those bluntly wrong predictions. And then in the end, we just simply don't append that to the mean prompt.
Okay, thank you. Cool. Any questions? Don't be shy. We can ask any questions if you like. Great. I guess, yeah, your solution is very great. So no questions.
Thankfully.
Yeah, thank you and congratulations. Okay, so let's move on to the next team then. Can I have a fourth team, please? Is that Yusuf to pull
Yeah.
up the presentation? Thank you.
Yeah, of course. Again, I'm a little ill, so bear with me. All right. Can you see it? Yeah, perfect. Thank you. Yeah, so mine is a little bit more terse, a little simpler to everything I've seen. But I guess that's probably why I dropped in the private leaderboard. So yeah, my solution basically is exactly what the last team just described as the simple model. But I forgot the slide. Let me introduce myself. So I'm Yusuf. I'm a data scientist at Adamenta. I'm originally from London, but I've been based in the Netherlands for nearly 2 years now. I've got a master's in applied stats, and I recently became Kaggle master, which on this cool feels a bit like that meme of the guy celebrating in third place or something. But there we are. So yeah, let's get into my solution. So it's very straightforward, and it was basically just a meme prompt. And the way I yeah did this is similar to what other people did. So like a greedy search on the tokens, based on the data I have, and then like sort of iterative refinement, because I mean obviously it's like a sentence embedding, so it doesn't really make sense to go one token at a time, because sort of adding, you end up getting stuck basically, because of well, because it's embedding the meaning rather than the individual words. One thing I actually wasn't sure about was this token Lucarea, which I didn't think it was analogous to the end of string token that that was mentioned in some of the other discussions. Like if you actually look up what it means, it's a Romanian word and sort of means like a lot of different things. So it means work, it means text, it means paper. And I thought in the context of sort of what you're trying to predict, like it tended to be this word that was really kind of sort of loosely defined, but agreed with everything that you were kind of trying to predict in that sense. And yeah, what's sort of interesting is that it's I guess it's in the tokenizer because it's a relic of when T5 originally came out. And I think the two use cases were translate, or one of the two use cases were translate English to German and translate English to Romanian. And then when ST5 was trained, it was trained on English only text. So it's sort of yeah, somehow kept its meaning based on that similarity. But yeah, anyway, yeah, what I ended up with was this meme prompt, and this meme prompt alone, I think this alone would have been second on the public leaderboard, and then I added Mistral at the end, for it sort of ended up giving me a little bit of a boost, sort of similar to what Philip had said in terms of, if you sort of think of this as the kind of intercept of the regression, and then the Mistral being the sort of smallest adjustment you could make. But yeah. So the way I did this was, again, similar to the other team. So I used Gemini for my prompt. I found one of the tricky things about this competition is that there was a lot of data that people generated, but a lot of it was a bit rubbish. And I found especially the stuff that GPT-4 generated was sort of quite robotic, and I mean, to be honest, a bit crap, right? Like, rewrite this quote as a quote to be quoted, right? That kind of thing. I think we all saw that. It seemed to love the word whimsical and put that in everything. It seemed to, ask about writing stuff in the style of Hemingway, right? And you dig into the T5 tokenizer. T5 tokenizer, it does have Shakespeare. It doesn't have Hemingway, right? Like so. I found using Gemini to be best here, and the rewrites. And actually, I ended up going with Mistral, but I also toyed with Gemma. I thought the original Gemma and Gemma 1.1 had huge differences. I thought 1.1 was performed a lot better, and actually I had similar results when tuning. And in the end, I the last thing I was sort of struggling on was whether to use Mistral or Gemma for the kind of final bit at the end. But in my submissions, they both did relatively well. So yeah, the way I sort of tried to get this was I actually tried to, I thought, well, what happens if I give a sentence in Latin or French, and then ended up digging into the T5 tokenizer to sort of see how it was decomposed. Yeah, as I say, it was initially generated by hard search on the next best token that maximize similarity, but then yeah, sort of iteratively refine them individually by going back. And I also did something similar to the team that spoke just before me, and I got like I think I generated. I didn't have a massive data set. I think I had about 5,000, and yeah, effectively took the scores that I knew were on the public leaderboard, took the scores that were in the public solutions, and effectively used a few different ways to try and generate a decent data set of about 1,000. So yeah, kind of top down, bottom up, and kind of genetic algorithms, these kinds of things, right? Like given the sum of the similarities that I expected, how far did it deviate from the individual ones, and penalize where there were massive differences. So that yeah, similar to what the last team said, that made a huge difference. Because yeah, as I say, the public leaderboard or the public data sets were not very good. Yeah, that's exactly what I just said. I probably should have been on this slide when I spoke over it, but yeah, that's basically it. And then I added Mistral at the end because sort of what I found was, and I think a lot of people had this issue, was that ST5 was sort of, if you were one word off on a relatively short sentence, even if the meaning was similar, you get penalized very heavily. But if you had that same phrase and appended it to a meme prompt, it ended up doing a little bit better. And that was the sort of reason I went with Mistral, and I prepended it with the sort of, modify this text by making it. I tested a few different variations, but these were all sort of in the T5 tokenizer. They scored quite well by themselves. And yeah, one of the other things that I spotted was the TensorFlow Hub ST5 and the PyTorch one had slightly different variations. So obviously you don't have the special characters. There are extra IDs that are also in the PyTorch one, which actually did quite well. I'm not really sure why, but they did quite well. And the TensorFlow one was capped at I think it was 128 tokens. It might have been 100. So this is something like 90 tokens, and then I had about 10 to play with in terms of getting somewhere a little bit closer to the final solution. This I think is the last slide. So as I say, it was very first. So yeah, I learned a few Romanian words because that's in the tokenizer. So that's a lot of fun. The adversarial method, so obviously to try and predict the embedding, I think give me a little bit of a boost. And yeah, trying to look at embedding similarities and trying to model that, it did give me a little bit of a boost, and I did try and kind of append kind of a hard search on the token on the mean prompt through this method, and I think that actually did score my best, but on the private, but it wasn't the solution. So that did help, but obviously, I think Team One said this at the start. You were sort of heavily constrained by the size. And I thought the competition ended up sort of being about the metric, which for me, it was my first NLP competition. So in a way, that's great because I would have done really badly otherwise. But yeah, it's sort of what I said. Like it actually is quite a good model for longer texts, right? So given a mean prompt and something appended that kind of pushes the embedding towards the general direction, that helped. But when you don't have that mean prompt and you have a very short sentence,